if you don't keep this in mind when you're warming up, you are more likely to get injured and you're not going to perform at your fullest potential. So, as always, I go to the physiology to explain things. So, I'm going to put myself on the side here and go straight from a lesson from my school community / course. But I'm only going to take a small chunk out of it, and I'm going to explain this very quickly and very simply so that you understand how to warm up properly. So first off, a warm up has the implication of what you're trying to accomplish in the term, which is to increase temperature. So when you increase your temperature, you decrease oxygen's affinity to hemoglobin. So if you dig, affinity just means how much something sticks to something. So hemoglobin transports oxygen from your heart to your muscles, right? And if you increase the temperature, you decrease oxygen's affinity to hemoglobin. There's a curve here too. So if you increase your body's temperature, you decrease oxygen's affinity, so that means it can more easily detach. So it's more easily released into the muscles, okay? And I'm going to come back to this because it's super important to understand, but this is a very important thing to understand about warming up. So the first thing that comes with the warm up is the raise in temperature, okay? Not only that, but when you raise your body's temperature, right, what happens? So not only do you decrease oxygen's affinity to hemoglobin, so you get more oxygen, and I'll explain why that's important in a second, but your joints are now more warm, so they're more elastic. As we get older, we lose elasticity in our arteries, and people get all kinds of diseases, they get clogged up. Same thing with our tendons. As we get older, they get more beat up. So it's more important to warm them up as you get older, right? When you're young, they're flexible, everything's super elastic. So if you increase the temperature, you increase the plasticity, so things are less likely to tear, okay? So static stretching isn't doing what you think it's doing as much as warming up. So what does warming up includes? It includes increasing your heart rate. So people talk about increasing your VO2 max or whatever. It's not that much. That's not as important as you think, by the way. But increasing your heart rate, actually, I don't know what the hell this chart is, but increasing your heart rate is going to increase your temperature, and you can tell what your max heart rate is just by subtracting your age by 220. So that's a guesstimate. Realistically, it's different for everybody. Some people have more efficient hearts, but you get your heart rate up. What's going to happen is your blood vessels are going to vasodilate. So a lot of the times we take beetroot powder whenever we want to work out, and you say like, whoa, like a lot of people have taken it and they're like, whoa, there were some real effects. The pre-workout supplement at my company has beetroot powder and L-citrulline, right? So we'll see a vasodilation effect. What happens when you open up a hose, right? More water gets let through. So in the sense of our arteries and our veins, which transport oxygen and blood to and from the muscles, you open up the floodgates for more nutrients, more oxygen primarily, and more clearing of metabolic waste, which I'm going to explain here in just a second. So if you are creating these contractions, which start at the brain, they start in the central nervous system, they go through the peripheral nervous system through action impulses, okay? So the difference between you activating multiple muscle fibers or fast twitch and slow twitch muscle fibers is how many firings you make. So a lot of these action impulses create larger amounts of force producing capabilities. So think of Tyreek Hill, Noah Lyles. They send out probably millions of these in any 1 second to activate all their muscle fibers at once, right? If you're ever doing a workout and you're like shaking, right? What's happening is your body is sending action potentials to certain muscle fibers, but they're not firing in serendipitous, not a serendipitous, in synchronicity, and one is firing here, but one is firing over there, and that's why you're shaking. So the adaptation there is to become more neurologically efficient, so you fire more in synchronicity, right? And that comes down to, let me see if I have the other page here, since we're on this topic. That comes down to these motor neurons, which transport these action impulses, becoming a little bit thicker, right? That pipe right there and that myelin sheath on the outside also becomes thicker. It's almost like a tube, which is like, it's like water. Imagine electricity going through water. Okay, so let's go back to the last one. So we're sending these action impulses, and in order to send these action impulses, there's not really a specific energy currency for action impulses, but there is a limit to them, and it has to do with like the dopamine that's in your brain, the serotonin levels. So your mood has a huge effect on this stuff, and we can get a little bit more into this later based on this let me see if I can find it here. We'll get into it right now. The fact that fatigue is very complex. So there's this governor of fatigue theory. We're going to get into this rationale, what happens at the cellular level, which prevents us from contracting. But from an action impulse perspective, think of it like electric currency. The currency comes from neurons and neurochemicals in the brain, like dopamine, and you know, it's very affected by our mood. So this is why we're not able to perform at our best whenever we have things that are stressing us in our life. And it's all intertwined and it's all interconnected, right? The human body is all interconnected, and it's actually quite simple. So going back to the currency for contraction rather than the currency for these electric impulses. So these electric impulses come from the brain, and then they go to activate the muscles, right? And the muscles, inside the muscles are these cells. And these cells, think of it like this. They're almost like, it's almost like Velcro, right? So Velcro, right? Velcro, the thicker it is, right, the more sticky it is. So if you inside your muscle can imagine these things are like gripping onto each other, right? And they pull to the center, and that is contraction. Like literally every single contraction in your body has like billions, zillions of these little muscle fibers. And small fact for you here, in order to grow the muscle, these things actually need to pull against each other so hard that they almost rip. We don't know exactly what happens in the muscle. There's actually multiple theories on what's going on. There's the winding filament theory. This is the sliding filament theory that I'm showing you here. This is the winding filament theory, which actually shows that muscles have the capability of being elastic, right? And this is very new science. But these are a couple ways we see it. We know for sure that inside the muscle, there's things gripping onto each other and pulling, okay? So that we know that for a fact, okay? So in order for that to go down, in order for this to go down and pull to the center, which is at the heart of every single contraction, we need the currency for that is, yes, the electric impulses, but metabolically, we need ATP, right? So ATP, just to show you, block this out so I can show you very simply. Let me see if I can actually present this in a cleaner format. So ATP is almost like a rubber band, like snapping, right? Because ATP, A3, so triphosphate, so adenine and ribose, and then triphosphate 3 will break off one of those phosphates. So the inorganic phosphate will break off, and that free energy from the breaking off will create ADP. So this ADP actually has that inorganic phosphate now that's just floating around, but you created the free energy, okay? So that is how every contraction happens, and you need so much ATP at any one moment in time, okay? And the thing that holds us back, people think lactate is acidic. No, that inorganic phosphate is what's acidic. Phosphagen, so phosphocreatine, this is why we take creatine, right? Glycogen, okay, so carbs, glucose, and oxygen and like fat all work together like so fast. We can't actually, there's a lot of people that say, well, you have your phosphagen system and then your glycolytic system and then you have your oxidative system that kicks in at whatever time. We don't really know this stuff. Okay? I've researched this very heavily, and I'm just going to tell you that it's all intertwined. You can't decide when you burn fat. You can't decide when you burn glycogen. It's a very automatic system, and as far as we can tell, it's all intertwined, right? But if you really want to read on it, there's some research that I did, and you can read on that. I'll simplify it for you. If oxygen is ever limited at any one time, think about it. People can, like, if they don't have oxygen to their brain, within how long do they die or have brain damage? It's like minutes, right? So it's just a little hint to show you that oxygen is at the heart of all this, right? So this is what I'm trying to tell you, right? In a fight or flight scenario, your body will reduce the amount of oxygen it sends to its organs in order to go to your muscles at any one moment in time. It'll also raise your heart rate, so you get more oxygen. So if at any moment oxygen is limited, what happens is ADP no longer gets turned back into ATP. Okay? ADP, which has that inorganic phosphate, which is acidic, no longer turns into ATP. And then we just don't have enough energy to fuel all the contractions. But remember I told you there's like millions of these fibers. Some of them will fire, some of them won't. So sometimes if you're shaking, it's because you don't have enough ATP to produce it in synchronicity. Okay? So this is how we get injured. Also, because one muscle is firing and the other one isn't. Your agonist is firing, the antagonist isn't there to balance it. Okay? A lot of people think that it's still lactate. Even very smart people like Matt from the movement system, this guy here who's super cool, right? There's no such thing as anaerobic, right? And this is a little advanced for a YouTube video, but realistically, it just doesn't even make mathematical sense that that would be going down. And the new research, like people like Andy Gallup and Evan Picon, who's a performance scientist, I even bought like Evan's course. I first heard about it from Buddy Morris, who's a strength coach for the Arizona Cardinals. And then as I did more digging, it started to make sense. Lactate is not acidic, and oxygen is what's needed to restore ADP back into ATP for maximum power output at any one moment in time. Okay, here's some more research that shows this. Here's some more evidence. So again, if you do not have enough oxygen to restore this inorganic phosphate back into ADP, really back into ATP, then you have bad contractions. Also, if ion gradients is like you don't have enough electrolytes, also what ends up happening is these the ADP also is not turned back into ATP. So electrolytes also take into account on the electrical side. So electrolytes are literally establishing ion gradients, right? So ion gradients is the difference in ion concentration or charge across a membrane. And when combined, these two forces form an electrochemical gradient that drives the movement of ions. This gradient provides potential energy that cells use to power various functions such as generating ATP in mitochondria. Mitochondria are the powerhouse of the cell because they process oxygen. So remember I was telling you, this shit's all intertwined. I mean, literally, I nerd out about this stuff. I probably could have told you guys, oh yeah, if you don't have enough oxygen, you'll fail easier at contractions. But it's very misunderstood for some people, and if you do a little digging, you see how important this is and why breathing through your nose, which increases nitric oxide production, will actually increase the amount of oxygen you have in your bloodstream. If you breathe CO2 out through your mouth, you can utilize your nose a lot faster, which is the reason we like to breathe through our mouth. And then you recover faster. You literally are more powerful for having breathed through your nose now. Do you see what I'm saying? So this is why I like to explain all these things. So I like to have a reason why. Maybe it's just because I grew up with around a lot of con artists. I had a staffing agency and I worked in the online guru space, and there was just so many of them. So when I fell in love with fitness, I really just had to get these explanations as to why these things are going down. Why, like, is this really what's happening inside the cell? And again, if you don't have this ion gradients, if you don't have the reestablishment of ADP back into ATP, you get these injuries, you roll those ankles. And again, fatigue is complex, but oxygen is at the center. Oxygenating work, so like on a low day, you can send oxygen to the muscles with 0 to 30% effort. The max effort you want to do on like a low day is like, 30 to 70% effort, because you don't want to strip energy stores from the muscle on low days too much. Max effort, stripping energy stores from the muscle and really placing damage on the muscle is like 70 to 100%, because the muscle doesn't actually have that much energy storage. It has some glycogen, it has some creatine, and this is why we know that having carbohydrates and creatine in our diet increase power outputs. But you don't want to deplete glycogen, you don't want to deplete energy stores too much, because what ends up happening at a cellular level, if you don't have enough energy, is like one thing will fire but the other one won't, and that's typically when things rip or tear. Okay? So understanding this hopefully gives you a better understanding of what to prepare for. All right, I don't know how many more slides I have in this lesson. This is a long lesson on athletic anatomy. If you want the full lesson, go check it out. The link will be in the description of this video to go join my community. And yeah, there's a free course for the first 100 members. And yeah, I'll see you guys in the next video.